Hello everyone. So welcome to this lecture number 4 for week 8 on the course on linear systems theory. So this will be a little short lecture where we will just list down the results for observability related concepts, essentially to do with the observable decomposition and so on. Very analogously to what we saw in the controllable decomposition, we defined a weaker notion of controllability called stabilizability, and then we derived results based on the requirement that I can stabilize the system if and only if the uncontrollable part of the system is a stable matrix, or it's a stable part. So essentially we could decompose the system into its controllable and the uncontrollable part, and much of the design was related to the condition that if and only if the uncontrollable part is stable, I can do some kind of eigenvalue assignment and so on with stabilizable systems. So we'll do something very equivalent with the concept of observability. We start as usual with an LTI system, could be in continuous in time or discrete in time, and which via a certain transformation T takes my matrix A to some equivalent A bar. So and similarly with B and C being transformed to B bar and C bar via this transformation C. So, so the result, which is again easy to derive, is the following, that the pair AC is observable if and only if the pair A bar C bar, where A bar and C bar come as a result of this transformation T, and so sorry, the pair A bar C bar which result as which come as a result of the transformation T is also observable. So that is like easy to check, right? Say assume that this A C is observable and it has a certain observability matrix C bar A bar. The observability matrix of this can be written simply as the, okay, let me call this O at O times T. Now if O is full rank, then definitely O bar is also full rank, because T I know is a full rank matrix. So this is like easy to check. So where we also had the similar result on controllability, where A B was controllable if and only if this pair A bar B bar was controllable, right? So again the proof is pretty straightforward. Okay, so so for every LTI system, so again we will ask ourselves, so the system is observable when the rank of this observability matrix is n. Okay. So what if the rank is less than n, right? So that is what we will answer now. So for every LTI system, there exists a similarity transformations that takes the system into a form which looks like this. This is my new A bar via a certain transformation T. B is decomposed into two parts, BO and BU, which is again the result of this transformation, and C looks something like this. Okay. So whenever I have a transformation like this, where the rank of rank of this O is now Q, which is less than n. So under such conditions, the unobservable space now is of dimension n minus q times n minus q. This is my observable space. So what I have done is via this transformation, which comes as a result of this O, I could decompose my system into the observable part here and the unobservable part. Okay. In such a way, now that the pair AC, sorry, A naught C naught is observable. Okay. So the A matrix decomposes this way, B decomposes into its own observable and unobservable components. Okay, this structure is not important, but what is important here is that the outputs now can be very easily decomposed So, I have a C naught here and a 0 here. You can also write down the dual version of this and check how the controllability properties of the dual system or the controllable decomposition of the dual system translates to the observable decomposition of the original system. Okay, so I leave it as a very small exercise. Okay, so what we know now is the decomposition into the observable and unobservable space, and that the observable pair is A naught C naught. Okay, so this can again just come as a result of a certain transformation where I can divide my states into the observable part and the unobservable part with a state space model which looks like this, right. I am just writing down these equations, plugging them into the appropriate x, u, y matrices and so on. Okay, so the discrete time version is also very similar. Okay, now since we know that the system is not completely observable, can we define a weaker notion of observability, right. I only know that certain states are observable, so maybe q states are observable and the remaining n minus q are not. So, can I define some weaker notion of controllability, and in that definition what are the things that I need to be careful of. Okay, so the definition goes something like this, that the pair A comma C is detectable if it is algebraically equivalent to a system in the standard form with n equal to q, right. So, when n equal to q, it would mean that the system is completely observable, right, which means this guy does not exist anymore, and then the unobservable space is just 0. Okay, so and okay, what if AU does not exist? It's a easy case, right, which is a standard observability case. What if there is AU? What if n is not equal to q? Then the requirement is that AU is a stability matrix. This one. Now, this one must be a stability matrix. So, what does it mean here is, so I have XO and XU. Okay. Now, these are the observable states, so I can construct them. These are the unobservable states. So, if I look at the second equation, I can write this as x2 dot is A21 XO, XU AU and so on, right. So, the expression becomes something like this, right. Now, what do I know is I know I can construct x naught, right. So, and I can write down the solution for the observable component. So, it turns out that I can write, so or I can also equivalently because x naught is observable, I can look at this entirely as some kind of input to the system. Because this can be determined, this is already known from the structure of the system, u is known, b is known. I just want to see what happens with this AU XU, which is unobservable, right. So, I can write down the solution now in terms of so okay, something missing here. This will be XU at T naught. Okay. So, taking this as the input, my XU takes this form, right. Now, what do I know is that A naught C naught is observable, okay, which means that I can reconstruct is okay, that this x naught can be reconstructed from the definition of observability, right, reconstructed from the input output pair, okay. And therefore, I can kind of construct this entire term within the integral, because everything is known. Now, for detectable systems, so when the system is detectable, we will look at what happens to this term. This term e power AU T minus T naught XU T naught. What is it for detectable systems? That AU is a stability matrix. So, when AU is a stability matrix, this term eventually converges to 0, right. This is for detectable systems. okay, and therefore, one can guess x u t naught up to an error which converges exponentially fast. Okay. So, what this means, okay, if I look at the opposite case where A u is not a stability matrix, so this guy will blow up to infinity, right, and therefore, there is some kind of instability within the system which is undesirable. Okay. So, the conclusion here also is that if the system is not completely observable, there is some hope of doing some design with the system if and only if the unobservable part is stable, right, and this is a little illustration for that. Right. Okay. So, the rest of the proofs are exactly the same as they look for the controllable decomposition case. So, the system is detectable if and only if every eigenvector of A corresponding to an eigenvalue with a positive or real part is not in the kernel of C. Right. Similarly, for the detectable case of a discrete time systems, you can do these proofs from scratch, or you can also write down the dual system and just compare with the controllable properties of the controllable decomposition. So, here if the rank of O is Q in the dual system, the rank of C, the controllable matrix of the dual system, which we I think denoted by a bar, will be Q, right. So, here the unobservable modes will show up here as the uncontrollable modes, okay, and so on, right. So, I think that duality is kind of a very useful concept here. So, I can just rewrite every result in terms of duality and then verify this, or I can also do it from scratch, right. Okay, then we have a similar version of the PBH test for detectability. Again, it looks exactly like very similar to what happened in the controllable case, or the controllable decomposition, or the stabilizability case. So, the last result here, which again I will just state it again, the proofs are kind of pretty easy to work out once you know the proofs for the controllability decomposition or the stabilizability case. So, the continuous time LTI system is detectable if and only if there is a positive definite solution to the matrix inequality, which looks like this for the continuous time and which looks in this way for the discrete times. Okay. So, just a little note on this thing. So, these kind of inequalities are usually called linear matrix inequalities. Okay. So, I am just giving you conditions on whether or not the system is detectable or stabilizable or controllable and so on. But I am not really telling you how to solve this at the moment, right. So, towards the end of the course on week 12, we will spend a lot of time looking at computational aspects of these kind of inequalities, which are also called as linear matrix inequalities. So, we will spend a lot of time there just to look at all these inequalities which we see in terms of Lyapunov stability, A transpose P plus P A being less than equal to 0, sorry, less than 0 and so on. So, we will spend some time actually finding out ways to solve this equation. So, I will also maybe introduce to you to some MATLAB packages which actually solve these kind of equations. So, if you are confused, oh, what do I do with these equations, just hold on, I will give you some very easy methods to check numerically how these work. So, if I give you say a 10 cross 10 system, it might be very difficult to check with hand, but there are some really beautiful elegant MATLAB packages which you can use, and I will eventually introduce you to those. So, to conclude this week, so we did a bunch of proved a bunch of results starting with definitions of observability and detectability, very similar to what we had for the controllable case. From the next lecture, we will start slowly building up on design concepts. A bit of introduction was given to design when I was talking about placing the eigenvalues at certain locations less than mu. That was somewhere in the previous week's lectures. So we will do all those procedures a little more constructive way, right? So which will be called as pole placements. So that's coming up starting next week. Thanks for listening.